Here at Michigan State University's Facility for Rare Isotope Beams, scientists come from around the world to experimentally produce and measure some of nature's most exotic atomic nuclei. Together with theorists like myself, we seek to answer fundamental scientific questions about the nature of rare isotopes and the nuclear forces that bind them. This understanding then lays the foundation for many different applications that benefit society on a global scale.
Promoting peaceful uses of nuclear technology, like nuclear energy and nuclear medicine, and answering big scientific questions like where were nuclei formed and the Big Bang and exploding stars. All these applications require predictive and uncertainty quantified theories of nuclear reactions.
But what are nuclear reactions? Imagine a projectile, a proton, an alpha particle, or a heavy ion. As we put it in an accelerator, it speeds up to energies between a few to a few hundred MeVs per nucleon. As it hits the target, several things can happen.
It can pass through without much interaction, scatter elastically or inelastically, or react with the target, like knocking out particles, transferring nucleons, fusing, etc. The detectors measure the ejected particles, but the question is, can we model the reaction without calculating what happens to every proton and neutron?
One solution is the optical potential. The idea is elegant. Instead of tracking every nucleon's interactions, we imagine the projectile moving in an effective potential created by the entire target nucleus. Think of it like this. When light passes through a cloudy medium, we don't need to keep track of every interaction with an individual molecule. Instead, we use an effective refractive index. Similarly, the optical potential is an effective interaction, a black box which captures the necessary physics without the need to track every microscopic detail. It reduces the complicated many-body problem to a simpler, effective two-body problem. The optical potential has two key components. The real part describes the average attraction or repulsion felt by the projectile. Crucially, the imaginary part represents absorption. When the projectile becomes close to the target, some of the incoming flux is absorbed into inelastic scattering and other reaction channels. The imaginary part accounts for everything that is not elastic scattering. So the optical potential is complex valued, and actually that's where the name comes from. In optics, a complex refractive index describes both the refraction and the absorption of light. Nuclear physics borrowed the concept, and the name came with it. Optical potentials have become fundamental to describing nuclear reactions. With a reliable optical potential, we can calculate scattering cross-sections for a wide range of projectile energies and different target nuclei. At FRIB, where we're constantly creating new isotope beams and designing new experiments, predictive optical potentials are essential to help us plan our measurements and understand their results.
Physicists are now building predictive optical potentials using microscopic models derived from underlying nuclear force. We calculate these potentials piece by piece by folding the nucleon distributions of both target and projectile with the underlying nuclear force. These potentials are exactly what we need at FRIB, where we study nuclei never measured before. This is exciting because it allows us to reach nuclear structure and reactions to areas that have historically been studied separately.
Building such potentials is now possible thanks to the advent of powerful supercomputers and new computational techniques. At the same time, uncertainty quantification is becoming essential. Until recently, optical potentials came with no uncertainties, providing a single prediction for the cross-section. Now, thanks to Bayesian inference, emulators, and machine learning techniques, we can construct bands of such potentials. Our predictions now come with error bars that tells us where we're confident in and where we need new experiments to guide us. These advances give more predictive power to nuclear reaction theory.
Nuclear physics research is fundamentally collaborative. In our research group, we collaborate closely with our colleagues at the University of Paris-Saclay's Laboratory for Nuclear and Particle Physics at JC Lab. We exchange postdocs and graduate students for several months at a time, exchanging expertise, discussing new ideas, and pushing the field forward together.
Thanks for watching. It takes a community to tackle nuclear physics problems. If you'd like to help, then consider joining us. Finally, if you are passionate about your own research, then consider making a video like this one to inspire future generations of scientists.